Okay. Well, good morning. About time to get going here. First, are there any questions about the Gauss's Law Lab that have popped up yet? None from you? Okay. There were some in the, I did get a message about one on Canvas, but
well, I was kind of wondering about question 2 in part 4.
okay, question 2 in part 4. Shoot, I printed that off yesterday. Can you read me what that question is? I guess I
Yeah.
put it up.
It's given a charge distribution that has some symmetry, construct a Gaussian surface that will allow you to determine the electric field at all points in the given space. Charge is distributed throughout the volume of a sphere of radius r equals 20 meters or 0.20 meters,
Okay.
isotropically such that the volume charge density depends on the distance r from the center of the sphere according to Br squared, B equals 85 nanocoulombs per meter to the fifth.
Okay.
Use Gauss's law to determine the electric field for positions lowercase r less than or equal to r, so the 0.20 meters.
Okay.
But I wrote Gauss's law out. I'm just having problems with units because the charge density is in meters to the fifth. And then you would have your radius that would be in that when you go and use Gauss's law for the area, you end up getting meters to the third, so cubic meters, and there's just some extra units around and I'm not sure where I'm messing up.
Okay. Let me actually print that page off and that may help. Let's see. Whoops, labs, not law or lectures. Where am I? There they are. And this is part 4, number 2, I think. Okay, and I'll just, maybe do a screen snip. Boy, I've got that indented weirdly, but that's all right. Put it on a new piece of paper. Maybe that'll be big enough to read. Hopefully. Oh, we'll switch over to that thing. And I am recording, so take that off. Okay, this one's a bit different, but usually when you're talking about a volume charge density, the volume charge density is going to be in units of coulombs per cubic meter. But the thing that you've got here is this constant, rho is equal to Br squared, that the constant is nanocoulombs per meter to the fifth. But that's because in order to get rho to be nanocoulombs per cubic meter, you need to have, you're going to be multiplying B by the radius squared, which is going to have units of meters squared. So if you multiply this B by meters squared, you'll end up with charge per unit or per cubic meter. That's part of it. But
okay. I think where I messed up is I substituted B as the charge density instead of the
Oh,
whole
and
expression.
instead of rho, yeah.
Yeah. Okay, that
And
explains a lot.
but you do have a sphere here, so you're going to be imagining the total sphere has a radius capital R, but you're going to be interested in finding out the electric field for lowercase r's here and at regions there. And Gauss's law will still work. You can still use the integral of E dot n hat dA inside that thing. You're not going to know the electric field, but the E dot n hat dA is going to be very much like, I think I did examples of calculating this over a sphere. So it'll look like that. You just don't know what E is going to be. But it'll end up being just, when you get done with this integral after a few steps, you'll just have E times 4 pi little r squared is what this side ends up being. The trickier part is that this, in order to make some headway on figuring out what E is, this is going to be Q enclosed over epsilon naught. And the charge enclosed is going to be a volume integral over this volume that has a radius of little r, and you want to know how much charge is in there. And so you'll be doing rho dV. And I don't know, in calculus, did they ever have you do any volume integrals or not? By the way, this V is, dV is a volume increment. And I don't know if in second or third quarter calculus they ever have you do anything like that. But
I think it depends on the instructor.
oh, okay. I remember doing them, but I also remember doing them a lot more in physics class than I ever did in calculus, I think. But dV, handy expression is that for when you have this nice spherical symmetry like this, you can just say it's going to equal 4 pi r squared dr. And so that would be the volume of the thing. Let's see. And rho for us is going to be this little br squared. And so if you substitute that in here, you're going to be doing something like b little r squared times 4 pi r squared dr. By the way, this is a volume element because this would be the surface area of a sphere. And then if you just imagine that a spherical shell, you imagine that that spherical shell has a thickness dr. And if you multiply its area by that little thickness dr, you do get the volume of the spherical shell. And if you integrate that all the way out from 0 to, let's see. Okay, now this is going to be a little confusing, but we do it in physics all the time. Your integrand will have lowercase r's in it. And that's one of the limits of integration that you're going to have too. So I guess you could call this one A if you want to, and then imagine different values of A. But and A would be just some intermediate radius of the sphere. And so you could do that. And then you won't have confusion between the variable in the integrand and the limit of the integration. But lots of stuff here. I mean, you get to do all sorts of calculations. Then I had, let's see, oh, I didn't print it, but that's how you would do that one anyway. So you will be able to figure out the electric field within the sphere. And then on the outside, it's just going to drop off like 1 over r squared, because from the outside, this thing will look like a point charge. So there's that one. Were there any other ones on the lab? Let's see, I can't remember. Somebody sent me an email about it, but they
On,
might.
on part 2, problem 3, when it says that E is equal to, what is it, BZ squared times K hat,
Right.
that is the electric field at every point. We can just,
Yeah, within that volume.
we don't need to add
actually.
together the electric field from every point to find that.
No, that's the
Okay.
total electric field at a point. And so,
Okay, so
and I
they've
think
done that for us, essentially.
Yeah,
Adding together and integrating. Okay. Okay.
Yep. I think I give you the value of B, if I remember right, or maybe I have you figure it out. I can't remember.
No, that you give us
It's
B.
given.
Okay, yeah. So, and then there was some stretch. That's the one with the cube, isn't it? That you have to think about. And there was some stretch where the electric field was 0, and you kind of,
Yeah, it's 0 from Z equals anything from below 2.
okay, yeah. And so here's this cube, and in part of the cube there is no electric field. And if this is, oh, let's see, X, Y. Whoops, that's not going to work. If this is X and this is Z, then yeah. So there's a stretch where the electric field is actually 0, and this may not correspond to the drawing that I've got on the handout, but in here the electric field can be 0, and then within this part of the cube the electric field has this dependence on distance, and so it's a totally manufactured situation. I don't know how you would actually do this, but somehow anyway. But that's the idea on that one. So if you're using Gauss's law to, I forget what, get the net flux or something like that of the electric field, since the electric field only points in this direction, the flux through faces like this one on top and this one around back and the one on the bottom, well, think about it. Remember, your n hat is a perpendicular to a surface. So, and what you know about dot products, I guess. Let's see, for the lab this week, I want, oh, there it is. I was wondering where I put I bought one of these multimeters that I recommended that you buy too. And I haven't actually had a chance to experiment a whole lot with this one, but to get it to measure resistance, you come over here. And last year I had I passed out some multimeters at school that the students used, and they had quite a different setup from these ones. So I'll have to record a little video of some sort that shows you how to use this. But the main idea is, if you're measuring resistance, you'll always have one wire plugged into the common ground thing, and then you look at the other things and see what they'll measure. And this one here measures milliamps, which is a unit of current. This one measures amps, which is a measure of current. And this 10 amp one, you only use this if you're going to be measuring large currents. So we'll never use that because we're staying with small currents. And so when we do measure current, which you won't be doing this week, we would just use this. This jack right here, if you plug the wire in there and then have the one here, you can measure V for voltage. You can measure the Greek letter capital omega is the symbol for ohms. And so these two are what you will use for measuring resistance. And the ones we used last year You just rotated it to an ohm reading, and then you pushed a button to determine which scale you were going to use. But on this one, you determine which scale by rotating it to various values in here. And I'll record something where I'll show you how that works. But the numbers that are on here tell the maximum value of resistance that you can measure on that scale. And so on this scale right here, I don't know if you can read it, but it says 600. And so that's the most amount of ohms that you can read, most amount of resistance. And right now I'm getting an OL symbol, and that's because the resistance between these two leads through the air is more than 600 ohms. And so that's why it works out. I still get an overload even if I go to the 60 meg ohm scale, that there's more than 60 million ohms of resistance through the air between these two jacks. So that's not surprising. So anyway, I'll have to do a little bit of a recording for you and post that lab this afternoon. Some of the descriptions that I have in the lab I used last year won't work for this one, so I may just cross them out rather than spending a few hours rewriting the entire lab. But that'll be for later anyway. Okay, yesterday I said at the tail end that I wanted to save this problem and do it today. And then we can also do this problem once we've done that one as well. And the idea is consider a ring of radius capital R with a total charge Q spread uniformly over its perimeter. And what is the potential difference between the point at the center of the ring and a point on the axis of the ring at a distance 2r from the center of the ring? Well, for starters, I will calculate the resistance at the center of a ring like this. Okay, where did I leave it? Oh, there it is. I'm trying to get organized about where I store all this junk. So just going to draw a circle here of radius capital R. There, that worked pretty well. Here's the center. Oh, I think I have a dead pen. Time for a new one. Wherever I keep those things. All right, so this will be capital R. And imagine that we have a total charge Q on this ring, and this will be in the plane of the ring. So this point here is the very center of the ring. And then we'll take this thing and look at it from a tilt and figure out the electric potential at points along an axis perpendicular to that. But for starters, we'll do that. Now, if there is a total charge Q here, evenly distributed, okay, I'm going to have to convert that into some kind of a linear charge distribution. But the circumference of this thing is going to be 2 pi r. And if that charge is evenly distributed along that circumference, then the charge per unit length is just going to be the total charge divided by the circumference. And so charge per unit length. So that's what lambda will be. Then I imagine some little increment of the thing here, and it'll have a charge dq, d lowercase q, and I'd like to know what is the electric potential at the center of this thing due to that little bit of charge dq. Well, One thing I could think of is, what if I have d theta, thinking about that, the length of this little circular arc is going to be r d theta, capital R d theta, because that's basically the definition of radian measure. So if I let ds be the arc length, equals ds, that's going to equal capital R d theta. And there are lots of different ways I could do this. I could just use ds as my variable and then just integrate all the way around the thing. But I'm going to do it with theta because I just feel like that this morning. And so we'll get that. Well, dV, the little increment to the electric potential, and this V is electric potential, not volume. The little increment to the electric potential due to that amount is going to equal K dq over R, where R is the distance away from it. And this is a scalar. It doesn't depend on which side I put that thing on or anything else. And so dV, since dq is equal to lambda ds, it's going to be lambda capital R d theta. So I'll have K over R, and dq is my lambda, my capital R, and my d theta. And the r's actually divide out here. And so I've got that. Let's see, what else have I got? Lambda is a constant. It's capital Q over 2 pi r, and K is that constant. So everything's a constant except theta. And if I want the potential at the center due to the entire ring, I just do something like this. I'll integrate dV, but dV is K lambda d theta. And the only thing that varies as I integrate around the circle is theta, so it's the only variable. So I'd have K times lambda times the integral all the way around the circle of d theta, and that's going to be 2 pi. So I get the electric potential is just going to be K times lambda times 2 pi. But lambda was capital Q over 2 pi r, and so the electric potential at the center of this thing is going to be K times lambda, whoops, not lambda, I want capital Q over 2 pi capital R times 2 pi. Well, shoot, that makes it easier. It ends up being K capital Q over capital R. Capital Q is the total amount of charge that's spread around this thing, and R is just the distance you are away from every little bit of charge in there. So it's kind of weird. It's like being a distance capital R away from a point charge, but instead you're at the center of a circular ring of charge that has that total charge on there. Well, this gives me some ideas about doing it for the case of a ring. Now we know what the potential is at the center of the ring. This asks, what's the potential difference between the point at the center of the ring and a point on the axis of the ring at a distance 2 capital R from the center of the ring? Well, this is going to take a little bit of drawing savvy, I guess, but not all that much. Actually, the thing that I want to get is the electric potential at any point on the ring. And so we'll go with this. And let the ring have a radius of capital R, like that. And I'll just imagine that I'm out here a distance. I could use any variable I want to. Maybe I'll use X. So this is my origin, and this distance out here is going to be X. And to finish this problem, I'll let X equal capital 2R, but I'll just do this. Okay. Something I'll be interested in is this distance here, which is going to be the square root of capital R squared plus X squared. And then I'll think about that some little chunk of charge here, dq. I'm going to use exactly the same thing that I did in the last problem. dq for that thing is going to be lambda times, I guess I could let it be lambda capital R d theta again. And lambda is still, for this situation, it's the same charge distribution. It's going to be the total charge divided by 2 times pi times capital R. But that'll be the amount of the little bit of charge there. I may just leave it as lambda R here for a minute. And that's what that will be. Now, the d theta is going to be down here in the this angle, measured from the center of the ring out here still. So d theta is going to equal capital R. What am I doing? Oh, this was supposed to be, yeah, lambda R d theta was the ds. So I'm not worried about it equaling anything, but it's this little angle here. So the little bit of addition to the electric potential that you get due to this little chunk of charge up there is going to equal dV in this case is going to be the K that always shows up, the little bit of charge, dQ, but the distance that we are away from it this time is going to be the square root of R squared plus X squared. Now, dq was equal to lambda capital R d theta. So I can rewrite that dv here as k times lambda capital R d theta. And I'm dividing by the square root of capital R squared plus X squared. So let's see, what do I actually have to integrate over? It's theta again. Everything else in here is a constant. X is a constant for this particular problem, and later when we get the expression, then we'll assign particular values to X. But V, then the capital V, the electric potential at this point, is going to equal the integral all the way around the circle here. So we're actually, well, I'll stick the limit on in a minute. K lambda capital R d theta divided by the square root of R squared plus X squared. And theta is going to take on values from 0 to 2 pi. So those are my limits of integration. But the only variable inside this integrand is theta. And that's the only place it shows up. And so outside the integral, I'll have k times lambda times capital R divided by the square root of R squared plus X squared. So as scary as this thing looked, the integral that we actually have to do is just 0 to 2 pi d theta. And that's 2 pi. So no big deal. Now we can substitute some things into here. The electric potential will equal K, that's a constant. Lambda is Q over 2 pi R. So Q over 2 pi capital R. And then I've got an R in there. That's going to simplify things. And then on the bottom, I've got the square root of R squared plus X squared. And when I integrate it around there, I got myself another 2 pi. And this R divides with that. This 2 pi divides with that. And I end up with the electric potential being K capital Q over the square root of R squared plus X squared. Again, it's as if this ring of charge represented a point particle that we were this distance away from, the square root of R squared plus X squared. So, and it's so much easier calculating electric potentials from charge distributions than it is calculating electric field, where you have to worry about directions and vectors and things like that. Then later, there's actually a way to calculate the electric field from the electric potential, but it takes partial derivatives, which is something that we don't necessarily expect you to do. And it's not always convenient. Sometimes you can get the potential for something like a pair of point charges, but to actually get the electric field, it can't be done in a nice, tidy way. And sometimes you'll get infinite series that are used, and depending on how much precision you want, you use different numbers in the infinite series. But we haven't figured out this problem yet. What's the potential difference between a point at the center of the ring and a point on the axis of the ring, 2r from it? Well, now that we know what this is, our value of x is going to be 2r. At the center, we just figured that out here. It was that the potential was K capital Q over R. At 2r from the center, I'll call this V sub C, and V at 2r, whoops, 2r, is going to be K capital Q divided by, I just have to stick a 2r in here and figure out what that's going to be. The square root of R squared plus 2r capital squared. And a little bit of work with that, that would be 4r squared plus r squared is 5r squared under there. It'll end up being K capital Q divided by the square root of capital R squared plus 4r squared, which is K capital Q over the square root of 5r squared. The 5 stays under the radical and the r can come out. So I'll end up with the electric potential at that point, 2r, is going to equal K capital Q over the square root of 5 times r. And the potential difference between these 2 points, well, this is the higher of the 2 potentials. It's going to be highest at the center, and then it drops off to 0 at infinity. So delta V would be that at the center minus that at the 2r place, which is going to be K capital Q over R times 1 minus 1 over the square root of 5, or 1 minus the square root of 5 over 5, which, I don't know, you could play around with this, write it a bunch of different ways, but that's enough right there. I'm not bothered by radicals in the denominator anymore now that I have a calculator. So that's it. That's all you had to do for that thing. But first we had to figure out that expression. By the way, they do this as an example in the book. And so it's sort of fair game to use that result, although you should quote where it comes from. So there's that. Then there's another problem that makes use of this. And it says the x-axis is the symmetry axis of a uniformly charged ring of radius r and charge q. That sounds familiar. A point charge, capital Q, of mass m is located at the center of the ring. So you'd take another point charge that has the same total charge as that thing. And then when it is displaced slightly, the point charge accelerates along the x-axis to infinity. Show that the ultimate speed of the point charge is that amount. Well, it may be disguised, but here's the idea. We've got this charged ring here, and for that thing, we'll have lambda is equal to capital Q over 2 pi r, capital R. And we'll put another point charge Q right at the center. Now it says when it is displaced slightly. Here's the deal. If you have that thing just sitting right at the center, it'll be repulsed by every part of the ring. But as long as it's in the plane of the ring, those electric field forces or the electric forces acting on it will be equally balanced from every side. But if you just displace the thing sideways a little bit, there'll be a component of those electric fields from all those charges on there that point that way. And so you just have to give it a tiny nudge and it'll be accelerated in this direction. And so, but the acceleration is not going to be constant. And so we can't use constant acceleration, but we can use conservation of energy. And in this case, the potential energy that it has at the center is going to be Q capital V. So here's our initial electric potential energy. It's going to be capital Q times V at the center. The final is going to be, for the electric potential energy, is going to be 0 because it will be at infinity. And when we developed the expression for the electric potential at the center, we were using the assumption that it would be 0 when you were infinitely far away from the thing. So that's the initial electric potential energy. Now, to that, I can add the initial kinetic energy. And that's 0 because it's not moving at first. The final kinetic energy is going to be some 1/2 mv squared that we don't know. We're just trying to figure out the speed on here. Well, what's the electric potential at the center? It was K capital Q over capital R. By the way, they're using, or when I wrote this, I think that textbook may have put a K sub E for the K that we're using. So that's okay. But we would have that initial electric potential energy being, or the electric potential being K capital Q divided by capital R. And so we've got that in there. Oh, they said it's a capital M mass. Anyway, this will end up being 1/2 capital M V squared. And looks like KQ squared to me. And if I multiply out from underneath by 2, I get that. And I'll have, let's see, 2 lowercase k capital Q over R, and if I divide by M, that'll be over here, and that's equal to V squared. And then if you take the square root of both sides, you get that expression. So this is a conservation of energy problem with a change in electric potential energy. And anytime you've got an electric potential V, and you want to know what will be the potential energy of some charge that you stick there, just multiply it by Q. Where we do that more often is if we have a potential difference, delta V, and we want to know what the change in electric potential energy of something is going to be. Well, Q delta V will equal the change in potential energy then. Delta V by itself is the change in electric potential. Q delta V is going to be the change in electric potential energy. And I just left the electric off of that. Usually in these situations, it's the only kind of energy that's going to matter, because gravitational just isn't going to have much of an effect. Okay, let's start applying some other things here. Let's see, a very long wire carries a uniform linear charge density lambda. Using a voltmeter to measure potential difference, you find that when one probe of the meter is placed 2.50 meters from the wire and the other probe is 1 centimeter farther from the wire, the meter reads 575 volts. What is lambda? Huh. Well, let's see. This is a complicated problem. Now, the hint here is to use the expression developed in the book for the electric field. This would be the electric field of a very long wire, which I know we did it last week with Gauss's law, but I forgot the result, which is not surprising. But I'll just use Gauss's law here, and I'm not going to talk my way through it. I'm just going to do it, and you can imagine what in the world is he doing. So this has a charge per unit length lambda. I'm going to imagine Gaussian cylinder of length L and radius R. Let's see. There, got it. And I actually wrote down a few more things than I usually would have, but the electric field is the charge per unit length divided by 2 pi epsilon naught R. So that's what I need to use here. At some particular point or distance R away from it, this is what the electric field happens to be. And for 2 different radii from here, by the way, this will point radially away from the wire if I happen to have a positive charge on it. So Now, the fact that when we're 2.5 centimeters from the wire, we get a 575 volt difference between that and 1 centimeter from the wire. Actually, I don't know which one's which, but I'm just going to assume a positive charge density. If it's negative, you could swap the leads, but I'm not going to worry about that. Anyway, the potential difference, when you know the electric field, the potential difference is going to equal the negative of the integral of E dot ds. Okay. I think that ds is the letter, S is the letter that's used, but in our case, we can just E dot dr if we want to. And if I look down the axis of this wire, so that's looking down the wire, the electric field points radially away like that. And so I can say it's in the r hat direction and ds is in the r hat direction too. So I'd like to calculate the potential difference at some r initial and some r final of E, which is going to be lambda over 2 pi epsilon naught r in the r hat direction, dotted with ds is just going to be dr in the r hat direction. Okay. A little increment of length moving away from the wire. R hat dot r hat is 1. And so my integral turns into the negative of the integral of r initial to r final of, well, let's see, lambda over 2 pi epsilon naught. And then dr over r is what I've got left inside there. This is a constant. And so my delta V ends up being the negative of lambda over 2 pi epsilon naught. And the integral of dr over r is the natural log of r. That should be one that's almost automatically after, or automatic by the time you're at this point, third quarter calc or better. So this would be natural log r final minus natural log r initial. I would tend to just go instantly from that to no. Okay, I'm doing this stepwise, but when it's the difference of two logs, it's the log of the ratio. And since I know this is going to be the natural log evaluated at these 2 points, which is going to be the difference of those two logs, it's going to end up being the log of the ratio. So I would tend to just jump right away to this thing, but I'm trying not to today. Minus lambda over 2 pi epsilon naught and natural log of r final over r initial. Okay. Now, our final is going to be 3.50 centimeters, because we start at 2.50 centimeters and go 1 centimeter farther away. So I'll have 3.50 centimeters over 2.50 centimeters here, and it's going to be a decrease in potential if lambda is positive. Okay, well, that makes sense. The electric field points in the direction of decreasing potential, and so as long as we've got a positive charge distribution with the electric field pointing away from the wire, moving away from the wire, you're going toward decreasing potential. And when you get to infinity, it's going to be 0. So that's the deal. We know everything here except lambda, and that was the question. Lambda for this one will equal, let's see, our delta V, I can think of that as being if I make the assumption that it's minus 575 volts, that it's a higher potential at R initial than it is at R final, then I'd have a positive value for lambda. But we're not given enough information to know. It just says one probe of the meter is placed 2.50 centimeters from the wire and the other probe is 1 centimeter farther from the wire. It doesn't say which probe is which. And on my voltmeter, if I'm measuring voltage, that's going to matter. Let's see, I ended up with 2 yellow leads for mine, I guess, but wow, these things get amazingly complex in just a short time. I think it's the second law of thermodynamics that stuff goes downhill. But anyway, there's my common lead. So here's, it says one probe and the other, and I stick them in points in space, but it doesn't say which probe is which. And so there's no telling if that, and especially the way I've got them twisted up right now, I have no idea. So if I got a 575 volt difference between 2 points in space, I couldn't tell because I've got twisted up leads which one was which. So I'm just going to go for the magnitude of the charge per unit length on the thing. And in that case, I'm going to ignore the minus sign. So I'll have 575 volts times 2 times pi times epsilon naught. And I'll be dividing by that natural log of, in our case, it's going to be 3.50 divided by 2.50, which sounds like 7/5, which I think is 1.4, but I'll leave it alone for the time being. The centimeters will divide out. And so that's what I'd get. And it's going to be kind of a messy calculation, but I'm just going to plug it in here, 575, and then I'll check my units. Times 2, where's pi? 2 pi times epsilon naught, 8.85 E minus 12 divided by natural log, where is it at? I haven't used logs on this thing in a while. I'm looking right at them, I'm sure. Oh, there they are. Natural log of 3.5 divided by 2.5. And I get a charge distribution of, I'll write it over here, 9.50, maybe. Yeah, that'll work. 3 sig figs times 10 to the minus 8, but I don't know what the units are. Actually, the only thing with units, I've got volts here, which are Newton meters per coulomb. And then I've got epsilon naught, which has units of Newton meter squared per coulomb squared. It's coulomb squared per Newton meter squared. And let's see, the newtons go away. One of the meters goes away. And one of the coulombs goes away, and I end up with coulombs per meter. Hey, that's good. That's a linear charge density. So there we have it. Okay. Well, that was kind of nice. Let's see, that would be 95.0 nanocoulombs per meter, if we wanted to write it that way. Then it says, if you now place one probe at 3.50 centimeters from the wire and the other probe 1 centimeter farther away, will it still read 575 volts? If not, will it read more than 575 or less than 575? Well, let's see. Our delta V ended up looking like this. Okay, lambda over 2 pi epsilon naught times the natural log of the ratios of the two lengths. For our ratios, we would have had 3.5 over 2.5. For part B, they're talking about having 4.5 over 3.5 in that natural log there. And as you get farther and farther away, this ratio is going to get closer and closer to 1. What's the natural log of 1? How about 0? Okay, we can check that just to be sure. Natural log of 1, 0. How about that? It's the exponent you would put on the stuff inside to get 1. Okay, but the deal is that as your, well, actually, we can do the natural log of 3.5 over 2.5 first, if you're not convinced. Okay, that one happens to be 0.3365, and then the natural log of 4.5 divided by 3.5 is 0.2513. So it gets smaller as the as you get farther away from it, and that's the rate of change of the electric field gets smaller as you move farther away, because it's depending on the 1 over r thing. And if you make a graph of 1 over r, r and 1 over r on the vertical axis, it ends up flattening out like that. So you pick a particular difference anywhere, and like here, say, a particular increment in the change in r, and then do the same thing here. And because the graph is getting steeper, you have a bigger difference in 1 over r from here to here than you do from here to here, and so forth. So there are many ways to look at that and try to figure it out. Let's see, question C on here asks, if you place both probes 3.5 centimeters from the wire, but 17 centimeters from each other, what will the voltmeter read? Now, this is a very long wire, so that won't be a problem, but the thing is, the potential between those 2 points, the electric field depends on the distance away from the wire, and it points radially away. But what you'll be doing in this situation is, here's our wire, our very long wire heading in this direction, and you're picking some point here where the electric field points away from the wire, and you're going to stay the same distance away from this very long wire. And so you want the potential difference between these 2 points that are the same distance away from the wire. Well, that delta V is minus the integral of E dot ds. And as you go along this thing, your ds is going to be perpendicular to the electric field everywhere. And when you're moving perpendicular to the electric field, the dot product is going to be 0 everywhere. And so there will be no potential difference here. So that's what's going to happen. Trying to think. For something like an infinitely long wire, you can calculate potential differences using this expression, but you can't calculate an absolute potential, because if you're wondering about the potential difference between some point r that you might start off at, the lowercase r, and infinity, Well, you do this integral minus the integral of from R1 to infinity of E dot ds. And E is going to point in the r hat direction. ds can point in the r hat direction. So you can end up with minus the integral from some, oh, we'll call it R1. Okay. R1 to infinity of, let's see, lambda over 2 pi epsilon naught r times dr. Well, so you're going to get the logarithm, but you'll have lambda over 2 pi epsilon naught with a minus sign here. And then the natural log of r evaluated at r1 and infinity. And the natural log of infinity is not defined. So when you have something like that, where it drops off like 1 over r, you can't use infinity as your 0 point for potential. You can calculate potential differences all day long between 2 points as long as one of them isn't at infinity. Now, in the real world, for practical terms, there's no such thing as an infinitely long wire. So eventually, when you get far enough away from this wire to where your distance away from it dwarfs the length of the wire, it's going to start behaving like a point charge. And at that time, the dependence on the electric field is going to start looking like 1 over r squared and not 1 over r. And instead of getting the natural log of r, then you'll get minus 1 over r that you'd be evaluating, which vanishes at infinity. But for the imaginary situations we're dealing with, where we're treating this as an infinite wire, it's okay to do the other stuff. Whoa, we went over the mark. That's okay. Tomorrow, I'm gonna, and probably Monday as well, I've got a series of problems that are challenging. They combine a whole lot of different things, but they also have at their core using electric potential for things. And these are mostly things that I've dug out of the, I think, your book for the most part. But they're things, the kind of problems at the end of the chapter that are not organized by section. They're the lump ones at the end. They're kind of hard and they're interesting. I find problems like that kind of fun. So the first one we'll do tomorrow is nuclear fusion in the sun, and we'll look at using what we know about electric potential to try and figure out some things there. So, and then we'll look at nuclear fission, how atomic bombs work, and I don't remember what all the rest of the problems I've got are. That's the nuclear fission. Yeah, mainly just fusion and fission, I guess, but lots of stuff. So, any questions on what we did today? You may have to rewatch that to absorb as much as you can. Let's see. Does anyone want to meet later and talk about the Gauss's Law Lab? And if so, what times might work for that? I can't do next hour because I've got Physics 114, but, and then when that's done, I'm going to take care of some details like uploading stuff to YouTube and linking it to your class. But by 1 or so, I could be kind of free.
I could do 1 o'clock.
1 o'clock works for Riley. Grayson or Philip, would those work for you?
I'm working all day today.
Oh, you're working all day. Okay. Do you have questions on the Gauss's Law Lab, or you know?
Yeah, I do have questions, but I'll ask them a little later today.
Okay. If you could ask them in text, that'd be okay.
Yeah.
But I'll be online at 1. Or Riley, could you meet later today?
Yeah, I get off work at 5, so
Oh, okay. Philip, would you be off work by 5 or do you work into the night?
Yeah, I get off at 5.
Oh, okay. How about would 7 o'clock tonight work?
6:30, 7, yeah.
That
Yeah.
works for me.
Okay. Let's do 6:30. That should work. So
Okay.
6:30 p.m. That'll work out okay. Okay. I'll see you guys then. And
Right on. Thank you.
I'll see
Have a
the
good
rest.
day.
You too. I'll see the rest of you tomorrow.